Some people say thermodynamics is the hardest class. Others swear it's fluid dynamics. But have you heard about heat transfer? And since it's final season, welcome to day 1 of heat transfer. Today, we're breaking down one of those radiation problems that looks harmless, until you see the triple integral at the end. We're given a graph of the spectral distribution of radiation from a diffuse surface. That just means the surface emits different amounts of energy at different wavelengths, and the graph is all we've got. The problem wants 3 things: the total emissive power, the intensity emitted in certain directions, and the fraction of energy leaving between 2 angle limits. So first, total emissive power. This part looks scary, but it's literally just area under the curve. The graph is a set of rectangular blocks. From 5 to 10 micrometers, the value is 100. From 10 to 15 micrometers, it's 200. From 15 to 20, back to 100. Multiply each height by its width, add everything together, and we get a clean 2,000 watts per square meter. Next, intensity. The question asks for the intensity emitted in the normal direction, and also 30 degrees from the normal, before we even think about a coordinate system. Notice the key phrase in the problem: diffuse surface. That is the magic word. Diffuse means the intensity is independent of direction. Or in plain English, intensity is the same no matter where you look. Normal, 30 degrees, sideways, all the same value. And for a diffuse surface, the total emissive power and the intensity are related by E equals Pi times I. So we solve for I, plug in our 2,000, and we get about 637 watts per square meter steradian. Question for you: where does this equation actually come from? And why do we need steradians? Drop your answers in the comments. Finally, we figure out the fraction of emissive power that leaves the surface, between pi over 4 and pi over 2 in the theta direction. Quick visual: theta is measured from the z-axis downward. So pi over 4 is halfway down and pi over 2 is sideways. These 2 regions is the zone we care about. So the fraction is the emissive power in that angular band, divided by the total emissive power. Mathematically, that becomes a triple integral over wavelength, phi, and theta. In the numerator, theta goes from pi over 4 to pi over 2. In the denominator, theta goes its full range. But because it's a diffuse surface, the intensity doesn't depend on direction. That means the intensity term factors out of both integrals and cancels cleanly. What's left is just a ratio of angular integrals. And after doing the calculus, or skipping the suffering like I'm doing, the numerator becomes pi over 2. The denominator becomes pi. And the final answer is exactly 1/2. Half of all emitted power from this surface leaves between 45 degrees and 90 degrees from the normal. Classic heat transfer exam material. If you're prepping for finals right now, save this video. Like and follow for more engineering walkthroughs leading up to the big week. Because some people fear turbulence, but heat transfer students fear solving triple integrals by hand.